So welcome everybody to the colloquium today. First of all, Happy New Year. First colloquium in the new year. Our speaker today is Tacconi from MPE in Garching. So Linda got her PhD at UMass, working at the FCRAO radio observatory on very early extragalactic CO surveys. She then moved on to Astron in the Netherlands as a postdoc, switching a little bit to H1 surveys with the Westerbork array and the DLA, and then came to MPE as a postdoc first, working on receiver technology for the JCNT submillimeter telescope, and then increasingly worked with the IRAM facilities, first and foremost with the PDPI interferometer. She then became MPE staff member, and today is leading, together with other folks, big extragalactic efforts studying the properties of the cold gas in galaxies throughout the universe. And on top of that, she is an ESO council member, she's an ALMA board member, she's a member of the IRAM Science Advisory Committee, and many more, so she has great insight into a lot of the millimeter and submillimeter business. And so today she'll tell us about some of these efforts related to molecular gas, star formation, and galaxy dynamics. So please, go ahead.
Thank you very much. Can you hear me? Is it too loud or too soft? Okay, so what I'd like to spend the next 45 minutes or so doing is telling you some results, mostly of the molecular gas contents of galaxies from the local universe up to what we would call the peak epochal galaxy formation range of 2 to 3. This is work that I am doing in part of fairly large teams, mostly with the FIBS consortium from IRAM, and those people are listed here, but also other programs, the cold gas survey in the local universe, and the KMOS 3D survey at ESO, which is an integral field spectrograph, which has 24 IFUs on the VLT. So we really can combine the information from all these different wavelengths, and I'll get into more detail of that later, but mostly I'm going to focus on the cold gas component, because as you see, it's basically what's driving all of galaxy evolution, at least in my opinion. So for the people who are not in this field, I don't know how many of you are doing things other than extragalactic work, but for the people who aren't doing extragalactic work, what I'm trying to do in the next 45 minutes is explaining two diagrams, basically. These are two fundamental relations of galaxies over cosmic time. And one is the famous Maddow plot, Maddow-Lilly plot, of the plot of star formation over cosmic time, where we know that the star formation density goes up from what we see in the local universe to a peak at around redshift 1 to 3, and then potentially a fall off from there, although I hear that it may not be falling off exactly like this. Another relation that seems to hold at all redshifts where we look is that there's a very tight relation between star formation rate and stellar mass, where you see a very tight sequence at all redshifts, redshift 0, 0.5, 1, 2, along this line, which some extragalactic people call the main sequence. This is what I will refer to as the main sequence of galaxy evolution. This is the star-forming sequence, but then down here there are also the cloud of passive galaxies, which sometimes is called the red sequence. So these two plots, we try to understand how did they come to be, what's driving this, and what I'd like to start with is first to give you a little bit background of what we know about the global properties of galaxies at this peak epoch, and then switch topics over to the molecular gas and how we're starting now with facilities like ALMA and the upgraded IRAM facility, NOEMA, how we're starting to learn about the molecular gas properties as well. And then I'll try to put this all together into one picture. Hopefully I can do that. So first of all, let me spend a little bit more time on this main sequence. What do we know about galaxies on this main sequence? Well, we know that it basically the form of this relation is the same at all redshifts. So here's a paper by Whittaker et al., which shows at various redshift slices, the general trend of star formation and stellar mass is the same, and the only difference between these different redshift relations is the offset, which means the star formation rate is, or the specific star formation rate, goes up in each redshift. So what's causing that? The answer, I'll tell you already, in case you have to leave or you're getting too tired, is the fact that we have more gas at these earlier epochs from which to form stars. The other thing we know about the main sequence is that most of this of galaxies is that most of the galaxies form their stars along this relation, along the main sequence. So that's shown here, where this line is what is denoting the main sequence. Here's the star formation rate, effectively the star formation rate density, and you see this little red tail here. This tail, which is the galaxies that are way up here, above the main sequence, makes up about 10% of the star formation. This is what people normally refer to as starburst galaxies. Galaxies which are undergoing an intense, short phase, must be short-lived phase of star formation. But although in redshift 2, galaxies on the main sequence have much higher star formation rates, they're still doing it at a very regular rate. It's not a burst. So that's the first point. High redshift galaxies are mostly not undergoing star bursts. They're just forming stars at a higher rate. What also happens is that at every redshift that you look at, basically once you hit a certain stellar mass, star formation shuts down at around 10 to the 11 solar masses. Something seems to quench galaxies and they stop forming stars by and large at those stellar masses. So those three things, those points, are things that we think are happening because of the amount of gas that the galaxies have. So the model that people are looking at now is what's thought of now as an equilibrium model for star formation. It's a balancing of different properties. So here you have a typical redshift 2 galaxy. I'll get into more. This is a normal galaxy, although it looks very irregular. It's actually quite normal. Or it looks a little bit washed out on the screen, but hopefully you can see that there's some faint emission here, and that there's a center here, but that the emission is dominated by these clumps. This is a multi-color image from the HST. So we're trying to, the picture of how galaxies evolve is one of equilibrium, where there's an equilibrium between the mass accretion of stuff, of baryons coming onto the galaxy. Once gas gets into the galaxy, stars are forming there, causing all kinds of interesting physics in its own right. Then in high redshift, we believe that structural transformations can take place very rapidly, such that clumps of clusters maybe can rapidly descend to the center to form bulges. And this is some work that Philip did in his thesis, Philip Lang, who's now here. And this is all balanced then by what's driving gas out of galaxies. So you have stuff coming in, and you have gas being locked up in stars, but then you have outflows, which could act to drive galaxies, gas out of galaxies, and ultimately things are leading to the quenching of galaxies and building up of the so-called red sequence that I talked about at the very beginning. So what we're trying to understand through all of our observational studies is this whole process. I will not spend any time on the accretion because that is very, very hard to do observationally. But I will try to spend some time on star formation, on the relations now that we're seeing with gas, and on outflows at the very end. So what are our tools? So if you look at a typical SED of a star-forming galaxy, at the long wavelength we have the millimeter regime where we can study the molecular gas and dust. With Herschel, we had, in the far infrared, we had a very good thermal calibrator of the total dust content of galaxies is shifted into the near infrared, we can study the ionized gas component, and then using the deep surveys from the HST with some SED modeling, you can get properties of the stellar mass. So we have quite a bit at our disposal, and up until recently, more time was spent in this wavelength. Herschel, of course, did lots of this wavelength, and now with ALMA and OEMA, we're spending lots of time to try to catch up. And I'll show you that I think we're rapidly catching up also at the longer wavelengths. So going back to the shorter wavelength, so for a minute, this is what a typical main sequence again from redshift 0.7 to 2.7 looks like as a star formation rate as a function of stellar mass. Here you see clearly the main sequence and a few outliers up here. This is what the underlying population looks like of thousands of galaxies from the HST. Now what can we add in our surveys? So with two of our surveys at MPE, there's the earlier survey called SIMS, which was 110 galaxies from redshift 1 to 3 with Symphony, some of which were done with deep adaptive optics resolution follow-up to give resolution of about 0.1 to 0.2 arc seconds. And now with KMOS, with the IFU, the new IFU KMOS, in a project led by, jointly led by Natasha Fürster-Schreiber and Dave Willman at MPE, there's now 600 plus, and they're almost at this goal already, of just purely mass-selected galaxies from redshift 0.7 to 2.7 with a very deep coverage in both stellar mass, star formation rate, and color, as you see here. This is the full sample on this plot. Where we're filling in now with our, the other survey, which I will talk to you in more detail about in a few minutes, our FIBS 1 and 2 surveys in Iran, where we've targeted 200 galaxies, selected just mostly on stellar mass. We have a fairly low star formation rate cutoff too, because we want to detect things. Selected again in this region, mostly at the massive tail. And we've stuck to more massive galaxies in these surveys for the simple reason that when you're trying to look in dust and gas, if you go to low metallicity, you lose your best tracers. This is an unfortunate problem which we will have to deal with as we want to push to lower masses, but both our CO molecule and our dust tracers, when you have low met, they're very metallicity dependent, and when you when you go subsolar metallicity, you lose your tracer. So we stuck to the higher mass end. Now, of course, IRAM is in the northern hemisphere, PISA was in the southern hemisphere, and so doing comparisons of exact sources is difficult, but at least in a global sense, we can make some comparison. So what are the near-infrared and the optical surveys showing us? What are the morphologies of these high redshift galaxies like? So what you can see is you see a variety of features. You see things that look fairly regular. You see some things that look somewhat red. These colors are actual real. So you can see some things at the high mass end that seem to have well-developed bulges. You see things that look very anomalous, where you would say, oh, this must be a train wreck. But actually, it turns out that that's not true in most of the cases. But the majority of them are what you would call clumpy star formation bright disks. Here's a close-up of one at redshift 1.6, where you see some of these RES-UV star-forming clumps. You start to see the central bulge region pop out when you go to the RES frame optical, and if you can make a map of stellar mass, it looks more centrally concentrated and less clumpy, of course. Now, Stein-Wölz in his work has done a very nice characterization of what the population of star-forming galaxies does morphologically by taking all of the Candles fields and combining it with the Sloan data. And basically what he's done is taken the main sequence and then figured out for each galaxy what the light profile looks like. So here you have n equals 1 exponential disks. In here, in the red end, you have spheroids, and in the middle, you have intermediate types. And what you can see is that, again, at all redshifts, along this main sequence, morphologically, these galaxies have exponential-like light profiles, and so seem to be disk-like. But of course, that's morphology only, and what we would like to know is what they're also doing kinematically. So that's what the KMOS 3D and SIM surveys have been doing. So here, what you see are velocity fields, the first moment of a data cube, where you're looking at the mean velocity. Now, for those of you who are not used to this, what you see here in red is the emission is red-shifted, and blue, the emission is blue-shifted. Now, what you expect from a galaxy that's rotating, whose motions, whose dynamics are dominated by rotation, is that if you put in a model here where you have an exponential disk, and then you measure a rotation curve, and you make one of these mean velocity fields, you would expect what's called the spider diagram. So these are contours of constant velocity, and then you see because you have velocity crowding at the center, you see a peak in the second moment in the velocity dispersion which drops off the radius. That's not to say that the centers necessarily have high dispersion. It's just that because you have this confusion from different velocity components in the center. So this is what you expect, theoretically, just a simple disk model. So you can see that in many of these cases, that's what you do observe. There are a few odd cases, like down here, where we don't know, maybe we don't have sensitivity, or maybe it really is a merger, but most of them look fairly regular signs of rotation. And if you do a quantitative analysis on this, you find that the majority, you can debate whether it's 60% or 80%, but it's well over half of the galaxies have rotationally supported disks. Now, these disks are somewhat different from the local disks. And why do I say that? Because once you subtract out the rotational component, if you look in the disks of these galaxies, the velocity dispersion, the mean three-dimensional velocity dispersion, is not 7 or 10 kilometers per second like it is in the Milky Way. It's more like 30 or 50. So this is a plot showing the velocity dispersion after removing this component. So it removes this central peak already. So we're only looking at the disks, far out the disks of the galaxies. And what you see is that locally you have a V over sigma ratio, or a velocity dispersion of about 10, which implies a rotation velocity to a dispersion velocity ratio of about 10 to 20. Whereas at high redshift, that drops to the dispersion velocity of about 50 and the V over sigma ratio of more like 3, 5, or so. What that tells you is that you have to take care, when you're doing an analysis of these disks, that you take care of the dispersion component. These are not nice, thin, Milky Way disks. These are puffy disks. They're very turbulent. But this means that in a disk where you have a marginally stable disk to collapse, you can easily show with a tumor criterion that you expect in a realm where you have a higher gas fraction, that the V over sigma ratio is inverse of the gas fraction. So if you have a very high gas fraction, you automatically will get a higher dispersion and a higher V over sigma ratio. I'll come back to that later. So what about the molecular gas? Now, so I've given you a sort of an overview, a rapid-fire overview of what we know about the near-infrared and the optical properties of these galaxies. I'll come back to that again at the end of the talk. So there are lots of new surveys starting. I'm going to focus mostly on the survey that we've been working on, that we've been leading with ION, called taking this data and using all the data that's available in the literature to try to explain the molecular gas contents of galaxies. So what the survey is over 200 galaxies from redshift 0.5 to 3, where we're mapping out the carbon monoxide molecule in its slightly excited 3 to 2 or 2 to 1 line. I'll get back to that in a minute. We've chosen galaxies just based on stellar mass, and we've chosen them in each redshift to be close to the main sequence. So we've selected above a stellar mass of log n of greater than 10.3 because of this metallicity argument. And what we've tried to do is, as best we can, cover parameters in stellar mass, redshift, and specific star formation rate. That is, the normalized star formation rate divided by the stellar mass of the galaxy. So it's a normalized quantity. So far, we're almost done. We've observed about 170 galaxies up until this winter, and we have about an 80% detection rate. We had a higher detection rate earlier on, but we did the easy stuff first. As we've gone to the harder stuff, our detection fraction also is dropping a little bit. So just again, for people who are not doing this as a regular basis, just a couple of minute aside on a fundamental property of what we're trying to do here. So basically, what we want is a molecular gas mass, but we cannot get it directly from the molecular hydrogen, because the molecular hydrogen, because it has no dipole moment, does not emit for the bulk of the molecular gas. So you have one of two ways to get around that. One, the traditional way has been to observe the next most common molecule, carbon monoxide, where then you get a gas mass. This is done. That's okay, I can go back to this too. Based on a conversion factor, which is determined through observations of local galaxies in the galaxy, which is basically a function of the density, temperature, metallicity, and the gas column density. And you observe, and this conversion factor has been calibrated according to the lowest, the ground state transition of the CO1 to 0 line. We know the alpha CO, is now called alpha CO or XCO, in the Milky Way quite well. And what we're doing in other galaxies is you try to observe the 1 to 0 line if you can. But what happens is that because as you go up in redshift, that 1 to 0 line goes out of the normal observing bands. But CO is actually great for this because you can actually go up the rotational ladder, and as you go up in redshift, you just observe a slightly higher transition. In most cases, that's okay. You don't want to go too high because then you're not probing the bulk of the gas anymore. But so you have to make assumptions to get your observed emission back down to the 1 to 0 transition. You have to make assumptions about metallicity corrections and so on. But then you can get your mass that way. Now, why is metallicity so important? This is the biggest effect, and it's the one that kills us at high redshift. CO has the property, so if you think of a very simple cloud, which is not what a cloud looks like, but you have an H2 size, a CO size. As you get to lower and lower metallicities, the H2 is still self-shielding itself, but the emission is able to penetrate deeper into the cloud and photodissociate CO. So as you go lower and lower to metallicity, so this is probably what you have. It's solar type metallicity. This is slightly subsolar, maybe 0.7 solar, 0.2 or 3. And if you go to really low metallicity galaxies, which you might expect in the earliest galaxies in the universe, you're basically going to lose your tracer altogether. But you can see what happens. Already with just a small change in metallicity, you're going to drop your CO emission quite dramatically. Now, lots of people have spent time on this in the local universe, but at high redshift, we don't really have it's something that lots of people are working on. So the second method is to use the dust. And you can do fits of assumed dust temperatures and do different dust emissivity models, and you then integrate under it, and you get a dust mass. You assume some gas-to-dust ratio, which itself is dependent on metallicity, and then multiply it by the dust mass, and you get a gas mass. Now that's what people have done with Herschel. And then more recently, a newer technique, which Nick Scoville and collaborators are spending a lot of time doing with ALMA, is if you're on this end of the Rayleigh-Jeans tail end of the dust SED, the dust is basically optically thin, and you can then take a single measurement and just directly get a mass from that, assuming you can cross-calibrate. You have to cross-calibrate to something. And that's the method, that's the limitation of that method. But so all of these will depend at some level on the metallicity. So you will have a problem. The advantage of this method is that it's much faster if you can do it. If you can get the time, it's much faster. We don't have Herschel anymore, so we can't do it. What's there is there. And CO, the advantage of CO is although it takes longer because you have to look for emission line, you also get kinematics for free, which is very important. So for the rest of the talk, I'm going to then show you are different surveys that we're combining. Our FIB survey with all these, with various other surveys at both low redshift, we have cold gas, the various Euler surveys on the market, the eggnog survey from Karma, then in intermediate redshift we have lots of information from Herschel and our FIB survey, and then at higher redshift there are various smaller surveys, including some that are being led up at NPIA, and then the ALMA continuum. So what we're trying to do now is to take basically all of these surveys together, and to try to understand the molecular gas history from redshift 2.5 back down to 0. So here we have a plot which shows the coverage along the specific star formation rate stellar mass plane. So this is the main sequence is at 0. This is this vertical line 0. So you can see where in redshift 0 we have very good coverage both above and below the main sequence. We also can go below 10 to the 10th solar masses with the new aspect of cold gas called cold gas low. At higher redshift, so the green spots are the underlying populations at the higher redshift. So you can see that we're biased to the higher masses, but we're also able now to get below the main sequence, starting to get below the main sequence. The different symbols, red are the dust measurements, blue are CO measurements, and black are measurements from 1 millimeter continuum observations to get to the gas masses. So what we have is over 1,400 measurements of either direct detections or stats that we can now use to analyze different relations of molecular gas as a function of redshift, as a function of stellar mass, and as a function of specific star formation rate or offset from the main sequence. So that's what I'm now going to show you are these relations. So the first relations are what we call the gas depletion time or the gas consumption time, which is only the molecular mass divided by the star formation rate. So it's just, if you do nothing else, it's the amount of time it would take with the current amount of molecular gas to consume all of its gas through star formation. This doesn't account for recycling, so it's a lower limit. So what we've done here with our 1,400 points, which are shown in green, and then we've done these bin averages in blue and red to show the different averages of the different techniques. Again, this is the Herschel SED dust method. Blue is always CO. There are different Herschel methods. This is green. These top three are green. The Herschel methods, the blue is CO, and the 1 millimeter dust photometry are here. So first, if you look at redshift, if you look at the redshift dependence, you see that the dependence fall off in all three methods is very shallow. And in fact, it depends on redshift with a minus 0.57 power. Now, the first thing you should notice is that although there's a lot of controversy in each of these methods, that the three different methods agree quite well, actually, when you plot the depletion time versus redshift scale. There are some little offset differences which we've corrected, but by and large, all will give you the same fit. Then if you take out that redshift dependence and you plot all the redshifts together, which you can do, and you then plot as a function of specific star formation rate, so here is the main sequence line, you find a very tight correlation of depletion time with specific star formation rate, which goes to this power. So we find it, and then if you take out that dependence and look for residual dependences in mass, you see very little. So as you go along from low mass to high mass, the depletion time, or sometimes people like to, the inverse of that, what sometimes people like to call the star formation efficiency, doesn't change much. There may be something happening at the low redshift end, at the low mass end, and this is all redshift 0 galaxies. But what we think that is there is that the metallicities have not been properly overcorrected, for. Now, what about the gas fractions? So you can do the other relation. What you're interested in is gas fraction. And here what we've calculated is gas to stellar mass ratio, just because we're doing everything in power law space, and it's much easier than to do it as a total baryonic fraction. So again, you take the same relations. You want to look as a function of redshift, specific star formation rate, and stellar mass. And here what you see is with redshift, you see this drop-off, which I'll come back to again, because the plot here doesn't actually show how steep it is. But you see this fall off from redshift above 2 down to the local value of about 10%. And then if you subtract out that dependence, which is here, you can look at the residuals as a function of specific star formation rate. Again, here is the main sequence at 0. And you see that there's a very strong trend, that galaxies above the main sequence have shorter depletion times, and they also have higher gas fractions, at least within the measured size. Then if you subtract that out and you look at what's left with stellar mass, here you do see a drop at the highest stellar masses, and that is seen, Amelie Saint-Onge in her papers at low redshift has shown this, and many other people are showing this, that it basically, as you go up in stellar mass, the molecular gas fraction drops above 10 to the 11 solar masses. So if you put this all together, the most important takeaway point on this part of the talk, what I want you to take away, is that star forming galaxies, or so-called SFGs, at the peak epoch of galaxy formation, are gas-rich. If you plot it, as I've done here, as a function really of gas fraction, so this here is no longer just a gas to stellar mass ratio, but a gas over stellar mass plus gas mass ratio, so it's a baryonic fraction. You see that here, at the higher redshift end, you have gas fractions that are typically half or even more than the baryonic mass of the galaxy, whereas in the local universe, it's more like 10 or 15%. So that's takeaway point number 1. Takeaway point number 2, then, is this offset, the difference that we see in the main sequence between this 0-point offset between redshift 0 and redshift 2 can easily just be accounted for by the fact that you have more gas. So you're forming more stars because you have more gas. And that, in this plot, this equilibrium model does seem to hold in general. We don't have the detailed observations at subgalactic scales yet. We'd love to get that. The other thing is that this increased gas fraction may well explain the fact that, naturally explains the fact that you get a higher turbulence, because the turbulence of a galaxy, the sigma and the gas fractions are related. So if you put this all together in one plot, what this shows, here is again a plot of specific star formation rate versus stellar mass in color-coded here's a color-coded plot of depletion time and gas fraction. You see that above the main sequence, up here, the depletion times are shorter. As you approach the red sequence, you get much higher depletion times. This is at all redshifts now. This is the redshift dependence taken out. And as you go for gas fraction, as you go above the main sequence, you also have higher gas fractions, which then drop as you go below the main sequence, as you might expect. Okay, so in the last few minutes, then, the last 10 minutes or so, I would like to then switch gears, not to what's happening inside the galaxies, to then what's driving galaxies out, what's driving the gas out of galaxies. And from that, what we've been doing mostly, this information comes mostly from the ionized gas observations, again, with Symphony or KMOS on the VLT. So what we observe in this typical star-forming galaxies in redshift 2 is we often see in the ionized gas, this is H-alpha emission, we often see evidence for broad H-alpha rings. This is the H-alpha line, here's the nitrogen 2 line next to it. And if you do a fit to just the broad component, which is here, you get this nice tail here, which is indicative of outflowing emission. So you have these star-forming clumps, which have star formation, which is strong enough to drive some of the gas out in an outflow. With typical outflow velocities of about 450 solar kilometers per second, typical outflow rates of about 1 to 5 times the star formation rates, but this is not quite high enough to push the velocity is not quite high enough to push the gas out of the galaxy. And we also see a very strong threshold effect. I'm only showing one example, but this is for tens of galaxies now that we see this effect where we have very high resolution observations. And that is that this onset, this is a plot of the broad over narrow component of the H-alpha emission line as a function of star formation rate surface density, so solar masses per year per square kiloparsec. And what you can see is this outflow phenomenon kicks in quite suddenly when you get to a star formation rate density of about 1 solar mass per year per square kiloparsec. So that is an effect that can influence, it can shut off the star formation in individual star forming clumps. Now, but what about if you want to quench a galaxy? You need to have a stronger outflow than what you typically can have from star formation. So what we've done there is actually looked in the centers of the galaxies, and we find that as you approach a log n star of 10 to the 9th, you see this broad component, right here in blue, in the H-alpha, in the majority of cases. So here's, for example, one plot which shows underlying the galaxy in green. Here's the narrow H-alpha emission, the narrow component, which you would say is due to H2 regions. The red is the rest V continuum, and the contours are the broad components. And you can see that in this case, where we have very good adaptive optics data, the outflow component is there is some in the disks, but the overwhelming, the brightest component is found in the disks. So if you compare then in tens of galaxies or hundreds of galaxies now, and you stack them, what you see is that in the inner regions, you see this broad component quite dramatically. In the outer regions, it's not that visible except for the star formation component. Now we also see it as a function. So this is schematically, you can see this as you put an aperture down in the galaxy and you look closer and closer to the center, you see the fact that the broad component comes up and becomes much stronger. These broad components are much, much broader than what I showed you in the previous slide. They can go upwards of 2,000 kilometers per second. We see them not only in the H-alpha line, but also in the nitrogen-2 and silicon-2 lines, and when we can map them, they tend to have a few kiloparsec extent. And there is an onset there at about 10 to the 9, 10.9. So this shows you the incidence of this phenomenon. If you plot the fraction of galaxies that have it as a function of stellar mass, here is the binned averages. Per bin, there's now 100 galaxies in the average, so you can see that at around 10 to the 10th, it's not very many galaxies that have it, and that number at around log n star 10.9 goes up to over about half or slightly more than half. So it's a fairly common phenomenon once you hit this mass limit. For comparison, if you want to say, okay, is this AGN fraction? These other colored plots here, this is the AGN fraction from the goods fields, the green is from cosmos, and you can see that this, our outflow rate is at least as high or even higher than the AGN rate. So we think that this phenomenon may last longer than AGNs. The AGN phase of a galaxy is fairly short-lived, but the outflow phenomenon may be much longer-lived. So what about the galaxy, or the molecular lines? We would love to do this in the molecular gas because that's, of course, the bulk of the gas in the galaxies in molecular form. So in the local universe, people have been doing this in ultra-luminous galaxies in AGN with both with the EROM interferometer in the brightest nearby galaxies like Markarian 231, and also with Herschel using OH absorption spectroscopy, where you see these broad wings in the OH absorption line. And here again you can see that the outflow rates are a few hundred kilometers per second, up to 800, and it seems to increase with AGN luminosity. The statistics are still somewhat low. But what we would really like is to do this at high redshift in some of our normal galaxies and molecules. And we're just starting to do this. So I'll show you two examples. They're the only two, I'll be clean, they're the only two we have so far. One is with Nuema, one is with Alma. So here is one of our redshift 1 FIBS galaxies where we've now integrated with Nuema at 0.35 arcsecond resolution. And here's the sort of red and blue side of the galaxy spectra, and you can see from this emission here, there's the hint of a wing in both the blue and the red components. This is super, you can't really see the contours. There's our sub-millimeter continuum map from Nuema, which is in contours, and the HST image of this galaxy is here. We are also able to show, here we can derive dispersions in the disks. We can show that it's also got a high velocity dispersion, just like the ionized gas. That doesn't, in the cases where we've been able to learn detailed kinematics in our molecular gas, the velocity dispersions in the molecules seem to be as high as the velocity dispersion in H-alpha. We have very small statistics, but at least in the first few cases, it doesn't look like the ionized gas is somehow different. We're also able to derive our rotation curve, which we plotted there. So this is one of, I'm using this as two examples. One is to show that we can now, with deep enough integrations, get outflows also in the molecules. But the other thing is that CO gives you so much more information than just the rest, because you get all the kinematics with it. Here's our ALMA map, which is our initial ALMA map. We're waiting for data from further data from the source. This is about 40 minutes of ALMA time, where we have On the top cloth, we have our Symphony Adaptive Optics map, which shows in green the narrow component of H alpha, in red the outflow component, and in blue the HST H-band image. And so you can see that there is a definite, I hope you can see up there that this red component looks like it's outflowing from the center of the galaxy. What's really cool, I think, is the ALMA map, which is at somewhat lower spatial resolution. It's at 0.7 arc seconds, but here again you see the narrow component of the CO in green and the outflow component in red. And you can see that the two of them look very similar, at least qualitatively. We've gotten time to go very deep and to go to higher resolution, so we can do a detailed comparison of the energetics between the molecular outflow and the ionized outflow. But those data have been taken, but we just don't have them yet. Anyway, so stay tuned. So I think that's basically pretty much on time. And those are the points I wanted to make about where we are with molecular gas. And so the takeaway points I will leave you in the summary. Those are that the high redshift galaxies are turbulent, much more turbulent and gas-rich than local spiral galaxies, with gas fractions approaching a half and dropping to 10% of H0. The star formation, the gas reservoirs for these galaxies track the evolution of the cosmic star formation rate, which in turn, we think, tracks the evolution of the accretion galaxies. So we think that this equilibrium model of galaxy evolution is describing most of the galaxies, at least from redshift 2 and lower. A technical point is that these CO and dust-based gas masses agree to better than 50% almost everywhere. So really, I think we're now getting statistics where we can cross-calibrate these different methods, so that just for a gas mass, I think we're ready to give up on CO. We use CO to follow-up work because we want the kinematic, but then to just get the mass, probably we can rely on the dust. We've derived quantitative scaling relations in the consumption time in the gas fraction with redshift specific star formation rate and stellar mass up to redshifts of 2 and now even beyond. And the elevated specific star formation rates above the main sequence at all redshifts are due both to high gas fractions and shorter depletion times or higher efficiencies. And at the high end, we see a flattening of the gas fractions, which also tracks the flattening in the main sequence. And that powerful outflows are ubiquitous in normal galaxies above a certain stellar mass, and this could play a role in quenching the star formation. So I'll stop there.
Thank you. So, questions?
So, a question to the connection between this turbulent disks, actually 2.5 and the Pacific galaxies. Two questions to that. Are these turbulent thick disks, are there any other thick disks contained? Do you think that?
That's a really good question, and we were hoping, you were at this meeting in Garching, where there was the disks meeting where people were showing lots of things from the local universe, and it would be great to get the people who are working on the thick disk to talk to the high redshift people, because we think that it's sort of a slow phenomenon that the thick disk is the remnant of redshift 2, but that it's a continuous thing. As the gas settles into these lower turbulent layers at intermediate redshifts, that you would then not have a distinguished thick disk, thin disk, but you have sort of a transition. But people in the Milky Way seem to think that there's something very different.
The second question, on the time of Milky Way, then the thickness would be relatively young, because redshift 2.5 is 8 gigahertz, something like that. It's not 10 or 12 gigahertz. which would mean like.
Yeah, but you see it also in redshift 1.
Yeah, the
I
second
mean,
point is, the second point is, for the really thin disk, we see an old population, thin old population of H10 gigabytes. And this should be there already. And you cannot cool a disk to get it thinner later.
yeah, it's a very interesting comparison. It's one that I don't think people aren't quite making enough the connection. And it's something that we should do more.
So, like,
When you show the outflows, many examples seem to be asymmetric. How many are asymmetric?
That's a hard one because we don't have the adaptive optics resolution for that many. I mean, we have adaptive optics maps of 35 galaxies, and of those, I'm trying to remember how many of those have outflows. Phil, do you remember?
No.
A few. I think it's a few. And what we're relying on then in the other ones is just the best seeing data in stacking. But we don't have the spatial resolution to say we're going to do a very, because that map I showed you is at 0.15 arcsecond resolution. That doesn't happen that often. Those maps take over a night of VLT time. Again, the tech does not like to give out time like that.
I see a slightly related question. I was trying to understand what is the difference between the H-alpha double-peaked broad components and the pedestal components. The double-peak, I guess, is a beam kind of outflow. You showed one example where it's very clearly, I think on slide 16 there. So some of them are even.
Okay, so these are the lines. So the H alpha is just the thing in the bright one. The thing next to it is nitrogen 2.
Okay, but so it's always a breadth of both pedestals.
So you blend these,
Okay.
you often blend these lines. Yeah. So you can do a separate fit for nitrogen 2 relative to the H alpha, but they're not in the pedestal, they're not totally.
So it's always a pedestal.
Because you can see the outer disk, they're not blended, they're separated. So you have the spillover, you have the outflow.
Regarding your outflows, your co-spatial outflows in H alpha and molecule field, do you have any estimate for gas masses in each component?
Yeah, that's the big question. We have been, I don't put a gas mass on there because first of all, we don't have the full data set yet. Second of all, I have to tell you, I really don't know which conversion factor to use there because the calibration of the CO conversion factor in the galaxy assumes the basis of that is that the cloud is a virialized cloud. We don't expect the bulk of a cloud in an outflow unless you have still some clump, but what's the state of the gas in an outflow? So we have to make an assumption about the optical depth, maybe in apply a variety, make an assumption that it's optically thin and calculate a mass. Make an assumption that it's virialized and calculate a mass. Make the classical Euler assumption that it's a smooth medium and calculate a mass and so they give a range. But we're waiting for the rest of the data so we can really look at the structure of the outflow before we, but yeah, that's.
so I have a short question. So you said for the ALMA data, which was 0.6 arcseconds, you get higher resolution?
Yeah, we had in cycle 3, we had a B-rated proposal which got time 4 days before the end of cycle 3, but the data we haven't seen yet. So that proposal was to do follow-on to take the 0.7 arcsecond map and to go deeper and to get down to about 0.2 to 0.3 arcseconds, depending on
What physical scales would you resolve?
So in redshift 2, an arcsecond is 8 kiloparsecs, so we're down to about 1.5 kiloparsecs.
Well,
It's hard.
yeah,
to go to higher redshift. We can go up, we see only the just use signal, or
The bulk of the gas is probably not traced by those higher lines, but the real problem is the metallicity. Because the mass metallicity evolution with redshift. So at a given redshift, the metallicity drops in a given mass as you go higher in redshift. So this is where people are trying to then argue to use ionized carbon. So the C+ line then becomes more interesting because it gets redshifted into the easier to observe bands. But then how to convert, you have a whole new set of calibration problems that people are working on. But it's, you have a whole other set of things you have to sort of understand to convert that to a gas mass is not.
but can you show me the metallicity distribution of your galaxies?
We don't have direct metallicities for most of them. You can, for the optical galaxies, you can use as a zero authority, you can use the H alpha to nitrogen 2 ratio and apply some calibration there. That only works if you don't have an AD, of course. For the CO, we don't for most of them. We have to rely just on the mass metallicity relation. But we don't have the optical spectroscopy, the rest frame optical spectroscopy that would be needed.
Next, a question about your nuclear outflows. So what's the evidence that this is an AGN phenomenon? Do you have continuing radio data, or?
No, it's not. That's what we're saying. Our point is that it doesn't need to be an AGN phenomenon. It's a black hole phenomenon. But whether or not there's an AGN that's on or not, it seems to turn on in a major way above a stellar mass close to 10 to the 11. So log m star of 10.9.
So what's the evidence for a black hole phenomenon?
Well, it's coming from the nucleus, so I
But it
mean,
could
most
be
massive
sensitive
galaxies
stars.
have a black hole.
But could this send the suffers or something like this?
That is something we can't yet rule out, but we would, in those galaxies where we see it, the H alpha to N2 ratios are very high, so it's probably not just a star formation. We are seeing it in various other excited lines. So again, it's not probably just star formation, and the average outflow velocity is higher than say the disk. When we look at the outflows in the disk, those are typically outer in the disk are typically 400, 500 kilometers per second. So the central ones are much broader. So it would be
It is a driving. I mean, it doesn't. The cost could be the same, but the driver could be different, right?
yeah, we cannot say for sure that it's not a very intense central starburst.
Does star formation drive 2,000 kilometers per second outflows?
What do you mean by star formation? I mean, it's a physical process, right? I mean, so you have basically cosmic ray driving the outer disk and some radiation driving the central part because of the thick. You could have sort of some different sort of momentum conversion.
I mean, it doesn't, to some extent it doesn't matter. Whatever the phenomenon is, if you can boost it up high enough that it can drive the gas out of the galaxy, you just need to be able to drive enough gas out of the galaxy. And if you have this, so the idea is that you have this conveyor belt that is bringing the high redshift and bringing gas in towards the center very rapidly. And then if you have some mechanism in the center that's then driving it out, you'll be able to quench that way. So it's a combination of what people call starving or strangulation, these horrible words that I don't like, and outflows. I think, again, often the discussion at meetings I've been to, people get very, it must be this or that, but I think it's a combination probably of everything. But whether there's some star formation like a very intense starburst.
and